Okay, let's see the contents of this video which I'm going to cover. First, I will explain what is the content-based image retrieval, CBIR. Then I will explain the MPEG-7 visual descriptors. Then I will explain the edge histogram descriptor, EHD. After that, I will explain the various steps to compute this EHD. And then we will discuss the MATLAB code for implementing EHD. After that, I will show you that how we can apply the EHD on images and how we can interpret its outcome. And then we will see that how we can use EHD for image retrieval. So let's go ahead. But before going ahead, I recommend you to watch following my previous video, that is the color layout descriptor CLD of MPEG-7 for image retrieval. This is another very popular and effective descriptor of MPEG-7 family. This video you can find from the link which is given in the description. So now let's go ahead. First, let's see what is the CBIR. The CBIR is also known as the QBIC, query by image content. It refers to the process of retrieving expected images from the large image database according to the contents of the query image. Here the contents mainly refer to the color, texture and shape features of the query image, which can be automatically extracted from the image using the various feature extraction techniques. The CBIR is different than the traditional search, which is based on the metadata such as the keywords, text or any description that is associated with the images. The keywords limit the scope of the queries because of the predefined or predetermined criteria, while the CBIR is actually the flexible, which is able to search on the contents of image rather than any predefined criteria. This is the overall CBIR process. I mean your image retrieval process. So here you have the image database which carries the hundreds, thousands or millions of images. We extract the features of these images with the help of some feature extraction algorithm, and then after that these features are stored in a feature database. Okay, now if we give a query image to the system for the image retrieval, we extract the same features of this image using the same feature extraction algorithm. Once this feature is calculated, this is compared with the previously stored image features in the database. Actually, we are doing a similarity check between the feature of the query image with the features previously stored in the database. So for the similarity check, we find some distances such as L1 distance, L2 distance, etc. And then on the basis of the minimum distance, we retrieve the most matching images as the output. So this is the simple overall process of CBIR. Now let us go through the MPEG-7 visual descriptors. The MPEG-7 is actually the standard for describing the features of the multimedia content. It provides the world's richest set of audio visual descriptors. With help of these descriptors, users can search, browse and retrieve the content more efficiently and effectively than they could use mainly text-based search engines. The MPEG-7 is an ISO IEC approved standard that is developed by the MPEG, of course, that is known as the Moving Picture Coding Experts Group. And this MPEG-7 formerly was known as the Multimedia Content Description Interface. There are actually the many descriptors which are the member of this MPEG-7 family. So they can be categorized as the color descriptors, which includes the dominant color, scalable color, color layout descriptor, which I have already covered in my previous video. That's why I was recommending you to watch this video. And then color structure descriptor, color temperature, G of GOP color, and the illumination invariant color descriptor. The next category is the texture descriptors, which includes the homogeneous texture, texture browsing, and the edge histogram descriptor. So in this video, I'm covering this EHD, edge histogram descriptor. And for the shape descriptors category, we have the region shape, contour shape, shape 3D, and the perceptual 3D shape. For the motion descriptors category, we have the camera motion, motion trajectory, parametric motion, and then motion activity. And for others, we have the localization descriptor, face identity descriptor, image signature, and the video signature. Now let us come to this edge histogram descriptor. It is one of the most popular member of the MPEG-7 family, which is widely used in the image retrieval process. So like color, the texture is also a very powerful low-level descriptor for image search and retrieval applications. So the distribution of the edges is a good texture signature that can be used for the image-to-image matching. To capture the texture feature, the MPEG-7 provides this edge histogram descriptor, which is useful when the underlying region is not homogeneous in textual properties. The EHD captures the spatial distribution of the edges. Somewhat you can say that it is similar to the CLD, where the CLD captures the color distribution. In a similar way, the EHD captures the spatial distribution of the edges. The EHD capture edges that are broadly grouped into the 5 categories. I mean the vertical orientation, horizontal orientation, diagonal at 45 degree, diagonal at 135 degree, and isotropic, I mean the non-orientation specific. Now let us see different steps of computing this EHD. So the first step is the image partitioning. The input image is first divided into 4x4, I mean the 16 non-overlapping blocks. Each extracted block is further divided into the 2x2 blocks for capturing the local edge orientation. So if image dimensions are not completely divisible by 4, then we have to resize the image so that the m/4, n/4 become integer. So this is how you can see. So you have an image of dimensions m/n. So it can be divided into total 16 blocks in the 4x4 grid. So obviously the size of each block will be the m/4 by n/4 block. So in my coming discussion, I will refer any of this block by naming this m/4 n/4 block. Okay, and this one block is further divided into small 2x2 pixel group. So you can see that there can be the hundreds and thousands of 2x2 combinations in one block depending on the size of image. And next step is the capturing the local edge orientation. So for each m/4 n/4 block, a 5-point bin is initialized as, I mean the bin equal to V, H, D45, D135, and NOE equal to 0, 0, 0, 0, 0. It means all the bin counts are initialized to 0. Here V bin count is actually representing the vertical edge orientation. H is for horizontal orientation. D is for diagonal edges at a 45 degree orientation. D135, I mean the diagonal edges at 135 degree, and NOE for the non-edge orientation, isotropic. And therefore, we have the total 16 bins for all 16 blocks, and each bin has total the 5 members. Okay, so we have total bins, bin 1, bin 2, bin 3 to bin 16. And if we keep all these bins side by side, obviously it will make the EHD vector, and its length will be of a t. So this is how you can observe this EHD vector, where all the bins are kept side by side. I mean from bin 1, bin 2 to bin 16. So this is the 80-point EHD vector. Now let us see how we can capture these edge orientations from this 2x2 pixel group. Now the local edge orientations from this 2x2 subblock is captured by 2x2 operators. So these are the operators which will be applied on this 2 by 2 pixel group. So this is operator 1 minus 1 1 minus 1 for vertical edge capturing. This is for horizontal, this is for diagonal 45, and this operator is for diagonal 135, and this is for non-orientation type edges. So what we will do this mathematical operation. I mean, simply we will multiply, I mean the element to element multiplication with this filter dk and with the 2 by 2 pixel group, and then we will sum all the values to get the orientation type. So here AK is your 2 by 2 pixel group, that is A0, A1, A2, A3, and this DK is your 2 by 2 operator, I mean D0, D1, D2, D3. So both will be multiplied element to element, and then we do a summation of all the values to get H type. So what we will do, we will apply all the 5 operators on one 2 by 2 pixel group, and we will have these 5 corresponding values of H type. I mean the EOV, EOH, EOD45, EOD135, and EONOE. So these 5 values are obtained. So this is simple mathematical operation. And now what we will do, we find the maximum of these 5 edge orientation. So we find the maximum of it, and then we compare this maximum value with some predefined threshold to get the dominant edge type. For example, let's say this EOH is the maximum, and it is also greater than the threshold. So we will say that the particular 2 by 2 pixel group has the dominant edge orientation of type horizontal. So when we get the dominant edge orientation, we increase the bin point, corresponding bin point y1. As we have seen that for first block, we define the bin as 0, 0, 0, 0. I mean all 5 types are 0 on initialization. So suppose for the first 2 by 2 pixel group, I get dominant edge type of horizontal, then what I will do, I will simply increase the count of this horizontal bin by 1. So the updated bin will be the 0, 1, 0, 0 like this. So we will do this same operation for all 2 by 2 sub-blocks in one M by 4 N by 4 image block. So obviously this count will increase, and at final you will get a bin like this. For example, let's say 500, 1000, 675, 20 sort of things. You get this type of bin value for one M by 4 N by 4 block. So this is one bin computed for one block. So now for one block, this bin is computed, and I can represent this bin for first block like this. I mean for first block, the bin can be represented by these symbols. I mean B0, B1, B2, B3, B4. So B0 is representing for vertical, this is for horizontal, and this value for D45, and this is for D135, and this is for non-edge orientation or isotropic. And the above operation is repeated for all 16 N by 4 M by 4 block, and therefore we will get the corresponding 16 bins. So when we achieve all the 16 bins, we can arrange them like this in another variable, all bins. So the first row is corresponding to your first bin, and that is computed for your first image block. So this is your second bin, which is computed for second block. Similarly, we compute the last one for the 16th block. Okay, so now we will find another important bin, which is known as the global bin. So the global bin can also be found by taking the column-wise average here. So if we take the column-wise average, we again get a 5 elements. And these 5 elements are known as the global bin. So global bin is simply the average of all the bins, okay? And if this global bin is combined together with all calculated bins, the length of the EHD vector now will be 85. Obviously, from bin 1 to bin 16, the length is 80, and this global bin also has the 5 points, so total length of EHD vector is 85. Actually, the main MPEG-7 EHD suggests only the 80 points in the bin, but I have personally observed through many experiments that if we go for the global bin also, the retrieval results are much better as compared to only the 80 points. So I recommend everyone to use the 85 points in this EHD with the global bin. And now let us go for the MATLAB code for implementation of this EHD. So first I will explain this simple program where we will apply the EHD on the two images and we will compare their outcome. So here in this case, with these lines, the first image is selected with help of IMRead. So your first image is IMG1, and with these lines you are reading the second image, image 2, and with the image read, your second image is IMG2. So yeah, you are reading two images, and now you are computing their corresponding EHD. So EHD1 is for image 1 and EHD2 for image 2. So now you are plotting all the images and their corresponding bins. So here with help of the subplot, I am plotting the first image, and then I am plotting its global bin also for the first image. Okay, so as I said that the global bin is the last 5 points of EHD. So obviously from the EHD vector from 81 to 85 are extracted as the global bin. And then we are plotting the second image and its corresponding global bin. So we can have an idea about their outcomes, so we can compare them. And in the second figure, I have plotted their EHD also on the same window to compare EHD of these two images, to have a look at how different they are with each other. And then here with these lines, I have computed the distance between the EHD1 and the EHD2. So first I am finding the L2 distance between EHD1 and EHD2 with help of this equation, square root sigma EHD1 minus EHD square. So the same output you can achieve from these lines also. I mean, you can use the MATLAB inbuilt norm function to achieve the L2 distance like this, and then displaying this L2 distance. And here with these lines, I am calculating the L1 distance between EHD1 and EHD2. And this is simply sigma absolute EHD1 minus EHD2, element to element difference, and then summation. And same you can achieve with this MATLAB's norm function EHD1 minus EHD2 comma 1, and then displaying this EHD. So let me run this program, but before running this program, the one thing we have missed, and this is this function. So here to find EHD value, I have used this function find EHD. This is not MATLAB function, it is my own function which I have written. So first let me see what is inside this find EHD function and how it is calculating the EHD of corresponding image. So let me jump to its explanation. So let us see the body of this find EHD function. So this is the function declaration. So image is the input and EHD vector is the output of this function. And with these lines, we are checking that input image which is passed as input argument to this function, whether it is a color image or the grayscale image. If it is color image, then we convert this into the grayscale using RGB to gray, otherwise we leave it as it is. And here with these lines, we are actually resizing the image to make it completely divisible by 4. As I said, it is not necessary that your input image is divisible by 4 from the row and column points of view. So we are just stretching it to make it completely divisible by 4, because we have to divide the image into 16 4 by 4 blocks. And here we are initializing all bins having 17 rows and 5 columns. Why? Because if you remember the previous slide, in all bins we arrange all the bins like this. I mean bin 1, then bin 2, and then bin 16, and in the last the global bin. So its size will be what? So total rows will be the 17, and the number of columns of course is 5, because each bin is carrying 5 points. So that's why we are initializing this all bins as 17 by 5 matrix. And here are some counterpoints to run a loop. So this is my for loop, which is running row wise 1 to 4, column wise 1 to 4. I mean to divide the image into 16 blocks of 4 by 4 grid. And this is how I'm extracting one m by 4 n by 4 block from the image. And this block is passed to another function, getBins. This is also not a MATLAB function. This is again my function which I have written. So in the coming slide, I will explain what is inside this getBins function. So this extracted block is passed through this function to get its corresponding bin, which is carrying all 5 points. I mean your vertical, horizontal, D45, D135, and then non-orientation type of edge. So this will be the output of the getBin function. So we will see in the coming slide. And here are some these counters. And then in the last, when all the 16 bins are calculated, they are arranged in this matrix. And to find the global bin, as I said, we will take a column wise mean of this variable all bin. So it will compute the global bin, and then we are appending that matrix by this global bin. So in the last we are attaching this global bin in the all bins. Okay, and since its size is 17 by 5, as I just shown you in the previous slide, so this EHD is in form of 17 by 5. So just to make it in a row form and a single form of 1 by 85, we are doing just reshaping. So we are reshaping into 1 to 85, so that by this you will get the EHD vector in single row. And now let us come to this function, I mean this getBin function, and let us see how it is computing all the bin points. So this is your function. Its input is the image block m by 4 n by 4, and its output is a bin of 5 points. So here again we are resizing this m by 4 n by 4 block so that it can becomes completely divisible by 2, because we have to divide, as I said, each m by 4 n by 4 block into 2 by 2 pixel groups. And here the bin is initialized. So this is your bin, which is initialized as 0 0 0 0 for all those 5 orientations. And here all the operators are described. I mean this is a vertical edge orientation operator, 1 minus 1 1 minus 1. This is for horizontal, D45, D135, and isotropic operator. And after that we define a threshold, as I said, because we will compare the edge type with the threshold. So what is this threshold? Actually this threshold is used to set the sensitivity of the EHD. If you reduce it, your count values will be more in the EHD vector, and if you increase it, your counts will be lesser in the EHD vector. So this is this threshold, actually you can say it's a sensitivity setting parameter for the EHD vector. I have implemented various image retrieval programs where I have found that t equal to 50 is working great. So you can put t equal to 50 and then defining the loop limits and setting few counters. And again, my loop is going from column wise and row wise. And then this is how we are extracting a 2 by 2 pixel group. Okay, so this is this block is representing this 2 by 2 pixel group, and on this 2 by 2 pixel group we are applying all the operators which are extracting the edge orientations. So the corresponding edge orientation values are going to PV, PH, PD45, PD135 and PISOT. As I said, we will get the dominant edge orientation by finding the maximum of these 5 values. So the maximum of these 5 will go into the value, and index will hold its corresponding locations. For example, let's say PD45 is maximum, so the value of the PD45 will go into value, and its index number, I mean the 1, 2, 3, 4, 5, I mean the 3 will go into the index, its location. And we'll compare this maximum value with the defined threshold. So if it is greater than or equal to this threshold, as I said, we will increase the bin count, corresponding bin count by 1. So as I said, if let's say D45 is the maximum and also greater than the threshold, we will increase the D45 count by 1. So this is repeated for all values 2 by 2 pixel groups, and that's why how we can find the EHD vector for a whole image. Although I could keep this getBins function and find EHD in the same program, but to make it a clean program or clean syntax, I have divided this code into the 2 functions. So I'm calling a function inside function. Otherwise, it will be difficult to make you understand with help of a single program. So now let me jump to the MATLAB and let me show you that how we can run this program and what type of output we will achieve for the different types of textures. So this is my program which is already written. So I will simply press this run button. So it is asking me to choose this first image. So I will select this image, let's say this one, which has the horizontal types of edges. So this is my first image. And now let me choose the second image. So I'm choosing this one which has vertical edge orientations. So let me see what output I will achieve. Okay, so this is my output. In the first graph, we are comparing the EHD1 and EHD2. So this is how we can observe that how the 2 vectors are different from each other. So this is not giving too much information. So the second image will give a clear picture. So this is the clear picture you can see. For this first image, see the bin count. So we have plotted the global bin as you can see. So the first column is representing the vertical edge orientation. This is representing the horizontal edge orientation. This is for D45, this is for diagonal 135, and this is non-orientation edges, I mean the isotropic. So this output is clear evidence of your EHD strength. I mean, you can see that it is saying that this particular image has the maximum horizontal edges. So that is evident from this image. You can see these all white lines are in the horizontal orientations. So that's why this peak, I mean the maximum value of this horizontal bin is validating it. Similarly, in this output, you can see that this first one is representing the vertical edge orientation, and same is validated from this image. This image is carrying the edges in vertical directions. That's why we are getting the highest value of this vertical bin. So this is evident that how the EHD is performing. So let us try on one more combination. So let me select few more images. So I am selecting this brick wall as a first image, and then as a second image let me choose this one, D49. Okay, so let's see what will happen. And this is the output, and this is the output. So here you can see in the first image we have a few vertical and the highest is horizontal. Obviously you can see that horizontal line is more dominant than vertical, and the second largest value is of an non-orientation type, because in between the horizontal and vertical lines we have this smooth area that is too much in entire image. That's why its value is highest. But now see this one, it has almost all the lines in the horizontal directions. That's why we are getting a very high peak of horizontal orientation, although it has some vertical edges also, so we are getting a very slight value of the vertical edge. So this is how the EHD is working, and it is capturing the edge of orientations in an image. So this is the effectiveness of your EHD. Now I will show you that how EHD can be used for the image retrieval. So here in this video, I'm not discussing the image retrieval implementation. I mean all that training and testing, etc. I'm just showing the testing of already implemented system. The implementation of the image retrieval probably I will explain in the coming videos. So here my aim is just to show that how the EHD is powerful enough to extract your images from relevant images from the database. So for that purpose I have chosen an image database which is known as a Wang database. So this is the Wang database, which is easily found on internet. It is used as standard in many implementations by the researchers. So it carries 1,000 images of 10 categories, and each category has 100 images. Okay, so I have applied this EHD on this database, and I will show you that how the EHD is effective in the image retrieval. So I'm just running this program, and here it is asking me to choose my query image. So I'm selecting one query image. Let me select this bus image number 307, and let me see what output I will achieve. Okay, so this is my output. You can see your this image is the query image, and this is the first match, this is the second match, this is the third match, fourth match, and this is the fifth match. So you can see its effectiveness on the basis of texture only. Okay, I'm not using any color information here. Okay, I'm using just texture. I mean the content of the image, no color. So on the basis of the texture only, on the basis of this EHD only, I'm getting this type of effective result. So let me try this on few more types of images. So let me select a dinosaur. So let me select this dinosaur, and this is the output. So this is your query image, and these are your first 5 matching retrieval of images from the database. So you can again validate its effectiveness. Now let me give another input. So I'm giving one let's say rose, and let's see what output I will achieve. Okay, so this is my input image, and these are first 5 retrievals. Mind this, again, I'm not using any color information, I'm using just the texture information. If I combine the color information also, you can imagine its effectiveness. So you will get more output matching with this color purple sort of things in this output. So this output is only on the basis of texture. So now let me try one more. So let me select, okay, one horse image. So I can select one horse image, and this is the output. So this is the input query image, and this is the first match, second, third, fourth, and fifth match. So this is how you can see the effectiveness of the EHD in case of image retrieval. So that's it for this video. I hope you have enjoyed it, and you have liked it, and you have learned a few new things. So I thank you all for watching this video. I request you to please like it, share it. In the next video, probably I will come with the image retrieval system, and I will try to implement the wavelets as feature extractor. So till then, goodbye.